9.3 Air Standard Diesel Cycle Processes. The air standard diesel cycle is an ideal cycle to model compression ignition internal combustion engines. The diesel cycle is very similar to the Otto cycle, but the diesel cycle compresses the air to high temperature to initiate the combustion. No spark plug is needed. In the diesel cycle, we have a high compression ratio ranging between 12 and 24. We use air standard analysis for the diesel cycle. The diesel cycle takes place in a closed system. The mass of air is fixed throughout the cycle. The cycle consists of 4 internally reversible processes. So let's see the processes on the TS and PV diagrams. We can see 2 isentropic processes, 1 constant volume heat transfer process, and 1 constant pressure heat transfer process. The location A is TDC, top dead center. Location B is BDC, bottom dead center. The only difference between the Otto cycles and the diesel cycle is the heat addition process, state 2 to 3. So in the Otto cycles, heat was added during a constant volume process. In the diesel cycle, heat is added during the constant pressure process. The remaining processes are the same for both cycles. Let's take a look at each process. Process 1-2. The piston starts at state 1. The piston is moving from BDC to TDC. It is an isentropic compression. The isentropic process is an adiabatic and reversible process. In other words, there is no heat transfer across the system, and no irreversibilities are present during the process. On the TS diagram, it is represented as a vertical line, no entropy change. The temperature increases. As you can see on the PV diagram, the pressure increases, volume decreases. Some work is done on the system. Energy balance equation for a closed system can be written. We are neglecting the changes in kinetic and potential energies of the system. We know that there is no heat transfer during the process. It is an adiabatic process. So the energy balance reduced. W12 over M is U2 minus U1. The work done on air is the specific energy difference between state 2 and 1. Process 2-3. At state 2, combustion takes place. The combustion process in the actual engine is approximated as a constant pressure heat addition process. The process is a part of the power stroke. The air expands and do the work. See the horizontal line on the PV diagram. The temperature and specific volume increase during this process. The combustion process is replaced by the heat addition to air from an external source. Using an energy balance, the work from state 2 to 3 is not equal to 0. The boundary work is integral of PdV. And the pressure is constant during the process, so we can write P2 times V3 minus V2. So Q23 divided by M is U3 minus U2 plus P2 V3 minus V2. So U3 plus P2 V3 U2 plus P2 V2. Since enthalpy is the sum of internal energy and boundary work, so the heat transfer to air is the specific enthalpy difference between state 3 and 2. Process 3-4. The power stroke continues. The piston continues to move until it reaches BDC. It is an isentropic expansion. The entropy remains constant. Again, there is no heat transfer during the process. Work is done by air. Using the energy balance, W34 is U3 minus U4. The work done by air is the specific internal energy difference between state 3 and 4. Note that power stroke includes process 2-3 and 3-4. Process 4-1 is a constant volume heat rejection. The piston stays at BDC. The volume of the air remains constant. No boundary work. Pressure and temperature decrease. Heat is rejected from the air. Heat rejection during process 4-1, U4 minus U1. The heat transfer from air is the specific internal energy difference between state 4 and 1. This completes the cycle.